Okay, so we are going to talk about the integrated rate law today. So for this lesson, you are probably going to want a calculator of some variety. And then the other thing you might want is your AP constants and equations sheet. If you have it, just a couple of these equations are on the sheet, so you may want to be able to find them so that you know where they are for later. All right? Okay. So integrated rate law is slightly different than differential because it expresses how the concentration of the reactants depends on time. So differential is how rate depends on concentration. This is how concentration depends on time. Okay? Whereas in differential, we did a lot of different experiments where we saw how changing our concentration would change our rate. In this one, what we're going to see, and instead of doing that, is you do one experiment over time, you record how concentration changes are measured. And then using that data, basically we figure out if it's 0, first, or second order, depending on how we graph the data and which graph produces that straight line. Okay, so we're going to dive in and start with 0 order. So 0 order, rate is equal to K. There is no it's equal to K, the constant, because the concentration does not affect our rate or how our concentration changes over time. So our integrated rate law for that is the concentration of our substance at time, whatever time, minus our initial concentration. So anytime we see that little knot, that little 0 knot, that just means initial. So initial right there is equal to negative KT. Now, this one is actually this formula is not tested on the AP exam, but it is important that you understand the graphing for 0 order reactions. So you don't need to understand the formula. We're giving it to you so you know what it is, but you need to understand the graphing. So for our 0 order, a plot of concentration of A versus time should produce a straight line with a slope of negative K. So we are looking for a couple things here. We are looking for that straight, linear relationship. And then the big thing is that it does have a negative slope as well. So, And so our slope is then equal to the negative of our rate constant. So for 0 order, concentration versus time produces that straight line with a negative slope. Okay, and since I don't really focus on the equation here, we're not really going to worry about it either. So we're going to go ahead and move on and talk about first order now. So just make sure you understand the graphing, and that for 0 order, it's concentration versus time. It's that straight line with the slope negative K. Okay, so for our first order, our equation is a little different. So we have our initial concentration or mass of our reactant, final concentration of our mass of our reactant. And our equation for this one is that the natural log of our concentration final over our concentration initial is equal to negative KT. Now, this one is on your chart, but it does look a little different than how we have it written here. So anytime we have things in natural log that are divided by each other, we can also just subtract them. So right here, we would have the natural log of concentration of A of our final temperature minus the natural log of the concentration of A at initial. That would be equal to negative KT. And I just said temperature, but I meant initial concentration. But because I wrote T, I said temperature. So ignore that, guys. So the natural log of our final concentration minus the natural log of our initial concentration is equal to negative KT. That's what's on the periodic table for AP. So it just depends on how you best would think through or work it, but you can use either one. So on this one, the plot of natural log of our concentration versus T, so the natural log of concentration versus time would give us that straight line. And then the slope is once again negative K. So we do once again have a negative slope here. And you'll see it's natural log of our concentration over time gives us that that first order reaction. Okay. So these you can actually have problems over this using the actual equation. It is on the periodic table, it is on your formula chart, which is on your periodic table. So let's work through one together. Okay. So it says, at 400 degrees Celsius, the first order conversion of cyclopropane into propylene has a rate constant of 1.16 times 10 to the negative 6 seconds. So that's going to be our rate constant. If the initial concentration of cyclopropane is 1.00 times 10 to the negative second moles per liter at 400 degrees Celsius, what will its concentration be 24 hours after the reaction begins? Okay, so let's see what we've got here. So first off, we have our rate constant. Right here, we have that 1.16 times 10 to the negative 6. So that's going to be our K value. Then we have our initial concentration. So we have A0, and we have 24 hours, which is T. Now, something to note here is that our rate constant is in seconds, but our time is in 24 hours. So we do need to go ahead and convert 24 hours into seconds for this problem. So I'm just going to pop up here and do a quick little dimensional analysis problem. So I have 24 hours. I know that 1 hour is 60 minutes. And then I know that 1 minute is 60 seconds. So it is going to be really important on the AP test or really just anywhere that you do make sure that your units match. So like if our time is in hours, make sure your rate constant is also in hours. So like in this case, our rate constant was in seconds where our time was in hours. So that wasn't going to work. Okay. But luckily we know how to convert between hours and seconds. So just quickly, we'll plug that on into our calculator. So 24 hours times 60 minutes times 60 seconds. And I got 86,400 seconds as our time. Okay, so we are looking to solve for our final concentration. That's what it's asking for. So it's like, what is its concentration? So that will be our final concentration. So let's go ahead and solve our problem. So our normal equation, I'm just going to pull it from the AP formula chart, is the natural log of the concentration of our final concentration minus the natural log of our initial concentration is equal to negative KT. So I want to solve for final concentration. So to solve for that, I'm going to add the natural log of my initial concentration to both sides. And so I end up with the natural log of my final concentration, having struggles writing this, is equal to negative KT plus the natural log of my initial concentration. I don't know why I keep wanting to put that O and the T inside the concentration instead of outside of it. I don't know. All right, so now we'll plug in our values. So natural log of our final concentration is equal to negative K, and our K is 1.16 times 10 to the negative 6 seconds to the negative 1, times our T, which is going to be what we solved for up there, 86,400 seconds, plus the natural log of our initial concentration, which is 1.00 times 10 to the negative second moles per liter. All right, so then we'll go ahead and plug that into our calculator and see what we get. So natural log of our final concentration is going to be equal to, we'll just start plugging it on in. So it's a dead calculator. So 1.16 times 10 to the negative 6 times 86,400 seconds plus the natural log of 1 times 10 to the negative 2. And I got, so when I plugged it in, I got negative 4.71. Okay, so now if I want to do the opposite of natural log, what I'm going to do is, if I want to get the concentration of A, so the concentration of my final temperature is going to be equal to E to the negative 4.71. So the opposite of natural log is raising it to the power of E. And the E button on your calculator is, at least on mine, it's right on the natural log. So second e to the negative 4.71. And I end up with my answer as my final concentration is 0.009 00 is what I got, and that would be moles per liter. And there you have it. That is how we solve that one. Okay, so it's just basically plugging in numbers. It just seems confusing since we're using natural log, but just remember natural log is just a button on your calculator. Okay, so now let's talk about radioactive decay. So radioactive decay is first order. So nuclear chemistry is not strictly tested on the AP exam, but nuclear decay is often used as like an example for kinetics. So it's kind of important to know that it's a first order, and also it's important to know about half-life. So half-life is the length of time required for the concentration of a reactant to decrease to half its initial value. So just to give an example, if I had like 4 moles of something, half-life would be the amount of time it takes for it to decompose till I only have 2 moles. All right, so that's our half-life. All right, and we do have an equation. It is also on the periodic table, and our half-life is equal to 0.693 over K, or your rate constant. Okay, so something to note is that a fast reaction will have a short half-life and a large K. A slow reaction will have a longer half-life and a smaller K value. So these are half-life, T1/2, and K are inversely related. Okay, let's work a practice problem here. And this one will be a relatively easy one. So the decomposition of SO2, and Cl2 is a first order reaction with K equal to 2.2 times 10 to the negative 5, 1 over seconds, at 320 degrees Celsius. Determine the half-life of this reaction. So we're just going to plug it in. So half-life, T1/2 is equal to 0.693 over our K value, which is 2.2 times 10 to the negative 5 seconds to the negative 1. Okay, so let's plug it on into our calculator. So 0.693 divided by 2.2 e to the negative 5th. And I got 31,500. And my K only has 2 sig figs, so my answer should have 2 sig figs. So that gives me 32,000 seconds as my half-life. Okay, so this next problem is going to be a combination of our first order reaction and our half-life. So I want you guys to solve for it. Now I'm going to give you a little hint. You do have to solve for K before you can solve for the half-life. All right, so that's your hint. I want you guys to try and solve it on your own. And then when you're ready, unpause the video. So pause the video now, unpause the video, and we'll go over it. Okay, but I want you guys to try to solve this one on your own. All right. Okay, guys, so first thing I did is I manipulated my equation to solve for K. So K is equal to negative the natural log of our final concentration minus the natural log of our initial concentration over our time. And so then I plugged in my values and solved for K, and I got 0.0373 1 over minutes. So then I plugged in that K value to our half-life equation, and I got that our half-life is equal to 18.6 minutes. All right. So we're going to talk about our last one, which is second order. So second order is, its equation is 1 over our final concentration minus 1 over our initial concentration is equal to KT. So the plot of 1 over our concentration versus time will produce a straight line with slope k. And what's kind of interesting to note here is that this one has a positive slope. So first order and zero order both have negative slopes, but second order does have a positive slope. So this is our equation. It's on the periodic table or your formula chart, and it does look exactly like that on there as well. Okay, guys, so what's really important is to know our graphs. So know which graph is going to produce a straight line for zero, first, and second order. So for zero order, it's concentration versus time. Second or first order, it's natural log of concentration versus time. And then second order, it's 1 over concentration versus time is going to produce those straight lines. Oftentimes, that's what we use to determine what order we have when we're using the integrated rate law. Now, knowing these equations and how to plug numbers into them is going to be good too. Most of the time, it's for first order reactions that we have to do it. So make sure you look over that. Okay, guys, I hope you have a good day. Feel free to reach out to Mr. Oglesby or myself if you have questions. Bye.